So let's continue with this. It's like we just showed that. So if I have a matrix summation, then basically I can diagonalize it. And actually, if you look at the proof here again, like we diagonalize that with the eigenvectors, right? Each time we look for eigenvectors, then we look at the space that is like orthogonal to the eigenvector, and then each time we just make one row, like zero out one row or one column of the diagonal elements, and keep doing that. I look for the another eigenvector and so on. So in the sense, I actually
so that is recursive.
Yeah, iteratively we do that. Like
Recursive.
Yeah, it's like half recursive as well.
Can be done by recursive.
And by the way, like actually another remark, we see that like we can use eigenvectors to diagonalize the Hermitian matrix here, and if we so in other words, like what we just talked about, that like if I have this matrix summation, then I should be able to look for eigenvectors like v1 up to vn and v1 vn. That's the transpose of that, Hermitian of that, and that will be able to diagonalize. Actually, it will be diagonalized exactly to the diagonal elements, so will be exactly the eigenvalues. And also,
That will be eigenvalues in there?
yes, there will be eigenvalues there. Actually, if you think of like here of course the thing is I assume all these three are kind of normalized, so vi always equal to 0, vi equal to vi is equal to 0. The norm of vi are all normalized. As we mentioned that like you scale eigenvector is still an eigenvector.
That's orthogonal then. That's orthogonal.
Your vi which sorry, it's not equal to 0. I'm sorry, it's equal to 1.
Yeah, it's equal to 1.
Yeah. Thank you. So therefore, like if you look at the diagonal term, for example, if you're a vi, the ith term, let's say lambda I mean the I diagonal element will be a vi times vi, something like that, right? So that will be equal to lambda I vi Hermitian, so it's equal to lambda I vi Hermitian vi, and that equal to lambda I, right?
Oh, yeah.
So therefore, like if you have the normalized eigenvectors here as the matrix, and then like these are all orthogonal, so this is supposed to be orthogonal, then you have, well, first of all, like if these eigenvectors are not orthogonal in the first place, I should say, like if the eigenvalues, for example, like lambda 1 is not equal to lambda 2, then we know that v1 will be orthogonal to v2, right? So we mentioned that earlier. And then like if like we have lambda 1, let's say equal to lambda 2, then I can have v1 may not be orthogonal to v2, but then like you can have let's say I assume that they are not linear dependent first, so I can basically make them orthogonal to each other, right? I can construct, let's say v3 is equal to v1 times some v1 plus, how do I do it? Let's see, equal to basically the Gram-Smith.
Mm.
So I want to have, okay, I have V1 and I have V2, let's say it's not perpendicular to V1. Let's see how to draw it. This is a V1, V2 here. Let's make something like perpendicular to that as V3. So then what I can do is I can have V2 minus the component of V1, so it will be like minus V2 V1, the inner product times V1. Something like that. I can construct this as V3. So then I can show that this is orthogonal to V2, right? Let's see, does it make sense? Let's see.
Orthogonal to B2.
Orthogonal to V1, maybe.
Yes. Orthogonal to V1 and
Yes,
V2.
yes, it's orthogonal to V1. No, it won't orthogonal to V2, but orthogonal to V1. V3 will be orthogonal to V1, right? Because V3, if I look at the inner product of V3 and V1, that will give me V2 minus V1. Sorry. V2.
Gram-Smith process will be orthogonal on both of sides.
No. You have like, you continue to do that. If you have more than 3, then you will orthogonal to 1 and 2. For example, like if I now I only have like 2 of them, right? I have this V1 here, I have V2 here. They are not orthogonal to one another first. So let's say I have like V1 now. I use the first one as V1, and then there's basically I want to generate spaces like V1 pi, V2 pi, and V1 pi orthogonal to V2 pi, right? Something like that, right? That's Gram-Smith, right?
Yeah.
And then basically I can pick like V1 pi is equal to V1, and then I can pick like this V2 pi is equal to this one. Then V2 pi will be orthogonal to V1 pi, V1 and V1 pi. Yeah, of course. Yeah, because V2 pi V1 is equal to V2 V1 minus V2 V1 V1, right? So we assume like V1 are normalized, so therefore like this is equal to 1, so that is equal to 0. So of course if you have like more than 2 vectors share the same eigenvalues, you can continue to do that. So you can do Gram-Smith, and then of course like these new vectors here will have to share the same eigenvalues lambda, right? So let's say if I have both V1 and V2 have eigenvalue lambda, then this new vector will also have eigenvalue lambda. V2 pi will also like eigenvalue lambda. So in any case, I can basically construct a matrix composed of eigenvectors of A, and this will be able to diagonalize A into the eigenvalues here.
Yeah.
Yeah.
This one. This because 1, and
Sure.
then for another one is eigenfactor also. So it means that this is the same. This is always the same factor. This one is always same factor with this one. Yeah.
Yeah, this is the same, but this has a Hermitian here. Yes.
Yeah, this Hermitian.
Yes.
So I think with just using this one or it is sufficient to create this.
But we need to ensure that it's orthogonal, right? So then we have the off-diagonal term is equal to 0.
Oh, orthogonality and
Yeah.
that.
And the off-diagonal term will be all this Vi, A, Vj, right? Let's say.
But this is we have done by a recursive process to create. You explain to us.
Yes. Yeah, I'm sorry, I can't confuse you. Like this I'm saying that like, if we ignore what we talked about like previously like just before the class, before the break, we said that like using that proof, like I actually it's like a recursive process. I show that that is able to continue to diagonalize that matrix. We know how to construct that V. But there, we didn't actually. This is I'm sorry. Like this is basically like an alternative proof.
Oh,
Yeah,
proof.
yeah.
Okay.
But this proof is not kind of as rigorous as like the previous one. Here I'm just saying that like a little bit more hand waving. Like if I have this matrix is constructed by the eigenvectors, and let's say if the eigenvectors all share different eigenvalues, then I apparently already have this, because they are all orthogonal to each other, those eigenvectors. Now, if I have some eigenvectors, if it turns out they share the same eigenvalues, I can still use Gram-Schmidt to make them kind of orthogonal to each other. I can construct a new basis or new set of eigenvectors, and those eigenvectors will be kind of orthogonal to one another. Yeah. So then I still have like this same thing here.
Oh yeah. Okay. So this is another explanation.
Yes. And yeah, actually. Maybe next time I won't talk about the previous proof. Like maybe it's a little bit redundant. I can continue immediately jump to this, but as you can see, if I have Hermitian matrix, then I can build eigenvector matrix such that A times eigenvector matrix. I'm also on the left hand side multiply the transpose of that is able to diagonalize that.
So that is the set of eigenvector matrix Vi
yes.
until Vn.
I know that like, because this is an eigenvector matrix, I have this, let's say I call this as a big V here. This big V times Hermitian big V times big V will be just identity here. Yeah, it's a unitary. What's this unitary?
And then there's will be not more than n, with always with the size is will be Vn.
Always by n? Yeah, because it's an n dimension, right?
N dimension.
You
depend to the A. So
yeah, this is a n by n here.
Can we find the more than n V?
No, you cannot, because it's an n-dimensional space, right? And that's only at most n vectors will be like orthogonal to one another, right? If you have like more than n vectors, definitely some of them will be kind of linear dependent to one another. Here is like orthogonal, right? So if they are orthogonal, they have to be all linear independent.
That's right. And then V actually is n by n. That matrix n by n, n times n. The
V is n by n.
Yeah, n
V is n by n. N by n.
Yes. And then and that should be eigenvector matrix.
Yeah, it's an eigenvector matrix. And by the way, like if you have something like this, is the reverse is true as well. If I am able to look for eigenvector matrix V and satisfy like A V times V transpose, V Hermitian times A times V is equal to a diagonal matrix, then this also implies that like A is Hermitian.
A is Hermitian, yes.
Yeah, let's see. So because if you have this, then you have like V Hermitian A V is equal to this diagonal matrix, and this diagonal matrix is Hermitian, right? So I have this. Okay, maybe I write like this. This is equal to D is equal to D Hermitian is equal to V A V Hermitian, so it's equal to V A V Hermitian A V Hermitian, something like that.
That should be Hermitian and there.
Yeah, because this Hermitian is equal to V Hermitian and the Hermitian times V Hermitian, right? That would give me just V here.
Oh yeah.
Yeah. So then I have this. I can multiply V Hermitian on both sides here, right? And because it's unitary, if I multiply V Hermitian on the right hand side, then I got cancel. I have A Hermitian V Hermitian is equal to V Hermitian A. Similarly, I can multiply V on the right hand side, then I will have like A equal to A Hermitian. So therefore, if I have basically this, if I can kind of like diagonalize A using a unitary matrix, then basically A will be Hermitian as well. So, and of course we talk about all this because we're interested to look into the real symmetric matrix, right? And real symmetric matrix is Hermitian.
That means that I still can understand.
Yes.
What we already have this one, and then what going to where? To this?
Okay. Here, like, if we have B A B equal to D.
D, yes, that's right.
So, and V Hermitian V is equal to identity. That basically V is unitary.
Yes.
Then A is equal to A Hermitian.
Hermitian.
So,
how to explain?
It's here. So, if I have like V Hermitian A V equal to D, because D is a diagonal matrix, right?
Yes, that's right.
And it's a diagonal matrix also with real eigenvalues.
Yes.
So then it will be equal to D Hermitian here is equal to V Hermitian A V Hermitian.
Yes.
I'm equal to V Hermitian A Hermitian V Hermitian will be just V.
That's right.
So I have this is equal to this.
Yes.
But like these guys are unitary, right? So therefore like V multiplied by V Hermitian is equal to identity.
V Hermitian V. Yes, that's right.
So I can multiply on the right hand side V Hermitian. So then this will get cancelled, right?
V Hermitian, yeah, that's right, cancel.
I can also like multiply a V on the left hand side, then like V Hermitian will get cancelled. So eventually I will have like A equal to A Hermitian.
Oh yeah, that's
Yeah.
right. So that's the conclusion.
Yes. So okay. That's basically saying that like this is a two ways. If you have like A is Hermitian, then you're able to find some unitary matrix to diagonalize A into the eigenvalues, set of eigenvalues. And also the other way around, if you're able to diagonalize a matrix into a real diagonal matrix, then that matrix has to be Hermitian as well. So this is all I like to talk about Hermitian. I'm sorry, this is some background in math. Now we can actually go to the actual covariance matrix, and wait, there's still one more thing it looks like. Let's see. Okay, one more thing. So if A is Hermitian, then okay, basically Hermitian is an extension of real symmetric matrix, right? So we can also define positive definite for Hermitian is we say something is a positive definite for A if like A's Hermitian AX will be bigger than equal to 0. This will be like positive semi-definite. X Hermitian AX is bigger than 0, then it will be like positive definite.
That depends to the A. If A is 0, that will be semi-positive definite.
Yeah, if it can be 0, then if it's possible to be. So now, since we can diagonalize A, right? So actually, A is positive definite if and only if all eigenvalues are bigger than 0.
Yeah.
And if like positive semi-definite, if and only if all eigenvalues is bigger than equal to 0. Yes. So let's look at maybe look at this one because the proof are similar, very similar. So if I have or let's say if I have like x is positive definite. Let's look at this way first. Say x is positive definite. Oh, sorry, a is sorry.
Eigenvalues is in D in there, so diagonal times that.
Yes, the diagonal lambda will be it's all here. So it means that all this will be positive. If positive definite,
There is no zero in there. All of should be
there
is no zero.
If it's semi-positive definite, it will be zero. But
will be some zero in there. That's right.
If it's some zero there, it will be like semi-positive definite. Yeah. If like there's none of them will be like zero or negative, then will be positive definite.
Yeah, that's right. So how to prove?
Yes. So first of all, I look at one way first. Like if it's positive definite, or like let's just focus on positive definite because either way, like the proof is essentially identical. So let's say it's a positive definite, then apparently this is apparent, right? This direction is actually really apparent because for any x, right, I can pick the eigenvector of lambda, right? So I can times vi. This will be equal to lambda vi Hermitian is equal to lambda, right? Assume vi is already normalized. And this is actually, we say that this will be bigger than zero, right? If it's positive definite. So therefore, like lambda has to be bigger than zero. Yeah. Now let's look at the other direction there. Like this is true for any I, right? This is true for any I.
Oh, so that should be lambda, and then positive definite should be more than zero. That is
Yes.
not different to the vi.
Let's see. Maybe I put the I here.
That is not depend to the vi. Just depend to the a, to the eigenvalues.
Does not depend. Yeah, does not depend on vi. Because I hear the lambda I pull out, vi we assume it's normalized, so it's equal to lambda I vi Hermitian vi, and this is just equal to 1 here.
Yes, that's right. Just depend to the eigenvalues.
We assume like everything normalized here. So so let's say like if every eigenvalues is like bigger than zero, then let's say if I have some I have x Hermitian ax. Now because A is diagonalizable, right? Because its Hermitian is diagonalizable, so I can write this as like so basically A, or like I should write what? A V Hermitian VA is equal to some diagonal matrix, right? It's essentially it's actually equal to lambda 1, lambda n, right? And then I call this D here. And then therefore A is equal to V times D times V Hermitian, right? So then I put it into here. So I have X Hermitian V D V Hermitian X, right? I mean like A is equal to V D V Hermitian, right? So I just substitute into that.
That's right.
So and this basically is equal to V X V Hermitian X Hermitian, right? Times D V Hermitian X. So these are the same, like those that these two vectors are the same actually. This is a diagonal matrix, right? This is a lambda 1, lambda n, something like that.
Oh, yeah, that's right. That is the same, just the Hermitian on there. So they become.
And so if I look at and if I look at this as a vector, so this is a vector, right? this is a vector. Maybe I just call it y here. I call this vector y. This is a basically y Hermitian here. So then this actually can be expanded as a lambda I y I lambda I y I complex conjugate times yi. Okay, does it make sense?
So then so will be so this will be d. The result of this will be d. That's right.
The result of this is equal to this guy here.
That's guy. How?
Where this let's see, should I try to expand that? Let's see.
What is this?
Maybe like let me get some intermediate step here. So this is a vector y and a vector y1 up to yn, right? Something like that.
Right.
So this is a lambda 1, lambda n, y1 to yn, and this is a y1 to yn, something like that. I'm actually a complex conjugate of that. Because I Hermitian, right? So a complex conjugate of each of this term here. And then like if you look at like let's say this multiplied by this guy, I will have like lambda 1 y1, lambda 2 y2, right? Lambda n yn, y1 yn, right? Because all the rest of the diagonal is 0, right?
Yes.
So it's like this just lambda 1 times y1 here. The second row is just lambda 2 times y2 here.
That's right.
Yeah, so I have this. So therefore, it will give me this one, right?
Okay. So this is written this times this.
Yeah.
This times this.
Yeah.
So this one, this one, this, and this one, this. And what is it? There's operation in here. No, this is a times. Yeah.
No, this is just a times. This is scalar now, right? This is just a scalar element.
Yeah. And
Y is just a scalar
multiplication. This
yeah,
one.
and this is of course it's a complex conjugate multiplied by itself. It's just a positive number. This would be positive.
Yes.
And if all my lambda is positive, then this will be positive, right?
Yes, that's right.
So
And some summation of this.
Yeah.
Summation of this. Summation.
and unless like this is like all 0, then it will be equal to 0. But if like this is all 0, then it means that the y is just all 0, right? Y is all 0, then x is all 0. Then of course we don't count. Actually, I didn't mention that like this is this should be positive definite. If bigger 0,
If y is 0,
x is not equal to 0. Right?
if y is 0, so it means that what?
If y is all 0, then x has to be all 0, right? Because this is just yeah.
So it means that
Because
what?
3 is invertible.
X is 0. So it means that what? It means that
Oh, let's not consider the y is 0 case here. It's not actually important. I'm just saying that this will be bigger than 0, right?
yes, that's right.
That's the whole point, right? This is if like all the lambda is bigger than 0, then this will be bigger than 0.
That's right.
Yes.
And then y should be bigger than 0 also.
Okay. If you have like some y, if any one of them is not equal to 0, then this will be still bigger than 0, right? I will have like this is equal to 0 unless all y is equal to 0, right?
Equal to 0.
I mean the y1 to yn, all of them is equal to 0, then like it will be equal to 0, right?
But if y is equal to 0, so it will be not equal to 0.
Oh, as I said, like
Set to 0.
no. As I said, like if unless like all all of yi is equal to 0,
Yes.
this will be bigger than 0. If y1 up to yn are all equal to 0, then this is just a 0 vector, right?
Yes, that's right.
Then what is x? X is equal to, x will be just equal to 0, right? Because x is just equal to v times y, right?
That's right.
So it's just equal to 0.
Yes.
So, of course, if your input is like 0, then that doesn't count. This is not something I should include that. Like I forgot about positive definite, because if you have some matrix times 0 times 0, of course this will be 0. This is not something we should we should count
so
on.
X cannot be 0.
Yeah, it should not be 0.
And then lambda it should be bigger than 0.
If A is positive definite, then lambda should be bigger than 0.
Yes, that's right.
So that's what we want to show is like if
Yeah, that's right.
so that's another way to kind of check whether a matrix is positive definite. It's just that you only need to check all the eigenvalues.
Yeah, just need to check eigenvalues.
Yeah, if all eigenvalues are positive, then it's like positive definite.
If there is lambda only 1 is same to 0, so it means that will be semi-positive.
Yes. And now we can really go to discussion to, I guess, have enough math background now. Can go to discussion for, yes,
Domain.
the coherence matrix again. So again, we have some x is a kind of like multivariate random variable. So I have x is composed of like, let's say x1 up to xn here. And now the coherence matrix, as we mentioned, that like I can write it in a compact form. It's just expectation x transpose like that. And we mentioned that this coherence matrix will be real symmetric. Sigma is real symmetric.
So
therefore it's Hermitian.
covariance is always estimation of x. Is there is x? It's
Oh, okay. I'm sorry. Yeah, I'm sorry. Like this is a I assume CO mean. So in general, it will be like is equal to
x minus b.
Yeah, x minus mu. But for convenience, let's assume CO mean. Otherwise, it'll get pretty ugly. But here we assume CO mean. So this is a general. So. And we mentioned a couple of things about sigma, the property of sigma. Sigma has to be real symmetric, therefore it's Hermitian. And also like sigma has to like semi-positive definite. Mentioned that. So therefore like, okay, what is saying that what we kind of like discussed earlier is that we know that now from real symmetric and Hermitian that like sigma should have like real real eigenvalues, right? So from here, we know that like we have real eigenvalues. And also like from semi-positive definiteness, all eigenvalues should be bigger than or equal to 0.
Yes.
Yes.
All. Yes. It means that all. It means that if what sum of that is
Yeah.
0 is that semi-positive.
If some of them are 0, it's a semi-positive definite. Yeah, but at least it has to be bigger than, it cannot be negative.
Yeah, cannot be
Or,
negative.
yeah.
there the eigenvalues has a negative?
No, it cannot be.
I mean that we can find for any case lambda is less than 0.
Oh, then it won't be a covariance matrix.
Yeah, it means that for another.
Yeah, of course you can. Yeah, of course you can.
Yeah.
Just for the case when we study this covariance matrix, the eigenvalue has to be non-negative.
So what's the case if it negative?
You can very easily construct something negative, right? For example, like this probably will give you a negative eigenvalue, right? Let's see. Is that? Let's see. Yeah, this will give you negative eigenvalues.
Why become negative?
Because you just look at this. This is the eigenvector, for example, right? This is eigenvector. Like 1, 0 is eigenvector. This multiplied by this is a minus 2, 1, 0, right? Yeah. So already you have negative eigenvalues. Yeah.
So it's something like the vector is different directions. Different directions with the one. That's right.
Maybe I'm not so sure actually. You can say I'm not sure like.
So we don't consider about that. What about negative one?
Here in this discussion we don't because it won't happen.
Okay.
Yeah. And let's say U1, Un are the eigenvectors for sigma. Let's call this. I don't know why I use P here. Okay, let's stick with the notation in my notes here. So let's say this is called a P matrix here. So it's like the V we have earlier. And then so therefore I can diagonalize this sigma with this P. So I have P transpose or P Hermitian now. Because if real symmetric Hermitian is equal to transpose, this is just equal to D.
So it means that real symmetric is Hermitian?
Yes, real symmetric is Hermitian. Yeah. Now I have this random variable is x, right? Now let's do a transform of this random variable to using a linear transform. Let me define some y here. Y is equal to simply P transpose times x. It's a linear transform of those random variables. So of course this is again some random variable, right? I can look at the variance, the covariance matrix of y. So let's write sigma y here is equal to just y transpose, right? So here because I also apparently y also has 0 mean, right? Because x has 0 mean, y will also have 0 mean here. So and this will be equal to expectation P transpose x transpose P. And then is equal to now these are basically like are not random variable, right? P I can put it out like P transpose expectation x transpose P. And now this is just the original sigma, right? So I have like P transpose sigma P. Of course P transpose sigma P is just equal to D. It's a diagonal matrix. So now yes. You see that after the transform, I'm making the y variable as basically is uncorrelated now. Y become uncorrelated because it just have a the covariance matrix is diagonal. So I basically have like expectation y yj is equal to 0, right? For any I not equal to j. Yes, that is a. If you remember, this is a. Of course, I have 0 mean we mentioned that in the past. How do I write that? This is equivalent to saying that yi and yj are uncorrelated, right? So you see that like if we can diagonalize the covariance matrix, we can use the eigenvector matrix to generate new set of eigenvectors. New set of random variables. Or no, I should say new random variable vector. That the random variable the random variable vector will be uncorrelated.
Where?
Mm-hmm.
At where?
Why?
I mean that your statement where in here to prove that.
Basically, x to start with, like it has a covariance matrix. It doesn't necessary to be uncorrelated.
Yes.
But if I can diagonalize this, let's say using the eigenvectors of sigma, eigenvector matrix of sigma, I diagonalize that. If I can diagonalize that, then I can use this vector to generate new set of random variable y here. Using just a linear transform, and we can show it here that the random variable, the new set of random variable will be uncorrelated, right? Because I basically from here I have the covariance of y is equal to 0. Not equal to the diagonal element, diagonal matrix, but it's equal to diagonal matrix, meaning that all the off diagonal term will be equal to 0, right? So that means that like I have expectation yj is equal to 0 for any I not equal to j, right?
Yeah, this is for any I equal to j, but if I is equal to z, it will be not 0.
Oh, of course.
Yeah, because that will be a lambda.
Yeah, that would be a lambda. But we just need that to say that like y are uncorrelated, right? Yeah.
But y is should be like this, cannot be any folds. That should be like this. Should be equal to b Hermitian.
Yes. It has. You
but if y is any is not like this, this is cannot be.
Yeah, sure, yeah.
Cannot be like that. So why we should be put in here like this? Why should be same?
Yeah, because we do that, then we are able to diagonalize the Hermitian, diagonalize the covariance matrix, right? And when you diagonalize the covariance matrix, you make all the y elements of y kind of like to be like uncorrelated to each other, right?
Oh.
Yeah.
Yeah, that's right. So you want to make that is diagonalisis. Okay, that's right.
Yes.
So would be.
And
when you be Hermitian times x, that will be can be diagonalized. Can be diagonalized.
you mean this one?
I mean that one. I mean that for that's y. For any x times by p, something like this. So it will be can be diagonalized, something like that. If this equal to this, if I equal to j.
Wait. I guess. Wait. A little bit careful. I guess here maybe my notation confused you. Y here is a vector. This is an n by 1 vector.
Yes.
And yj here is a 1 by 1 element.
Yes.
Right. So and you if you say I equal to j, that's saying that like when you compute I equal to j is computing variance, right? You're not computing covariance.
Yes. Variance only one.
Yeah. Basically, you have like expectation yi square, right? You're computing yi square, right? This is actually computing the variance, right?
That's right.
The sigma I square. That is actually equal to lambda I.
Yes, that's right.
And actually, that's one thing I want to mention. Why we want to have covariance matrix to be not just semi-positive definite, we want it to be positive definite because when it's semi-positive definite, it means that like some of the eigenvalue will be zero, right? And most the eigenvalues, the physical meaning of the eigenvalues is actually the variance. So that means that in some particular components, actually the variance is equal to zero. That means that that one is actually not in that component. It's not actually a random variable, right? It's actually a constant. So it degenerate to a case is actually you mix a constant with a set of random variable. So since it's a constant, you can pull it away, right? It's not really a random variable. We don't need to consider that, right? So therefore, in practice, it's safe to assume that like you have all the eigenvalues are actually positive, or like the coherence matrix is positive definite. Yeah.
Positive definite. And an x and an x in here is any, can be any.
X can be any here. Just here we didn't assume like x to be Gaussian yet. We just assume x. We didn't assume anything actually. We say x is just a multivariate random variable, right? Yeah. So x1 up to xn they can be kind of correlated somehow, but we don't know what kind of statistic is that, like what kind of distribution does it have. We only know that okay, we can compute the coherence matrix, and okay, here we also assume that it's zero mean. But even though like, it's not zero mean, you can subtract the mean, right? You can always first subtract the mean. It doesn't matter. Actually, it doesn't change anything. And once you subtract the mean, then then since the coherence matrix is positive, definite, and symmetric, then you can like diagonalize that. You use the eigenvector matrix. You can generate to create a linear transform to generate y, and the new set of random variables they will be uncorrelated.
Yeah, that's right.
And actually,
that's a linear combination.
Yeah, this is just a linear combination. Yes.
Oh yeah, because that's like that.
Yes. So it's pretty nice. I guess some of you probably heard of PCA, like principal component analysis. So what we are doing here is basically just PCA. We kind of
we make some reduce the dimensions.
Not yet. We can reduce it afterward, but we have a linear transform, right? You have y equal to p transpose a. Sorry, not a, p transpose x. You kind of like do a essential rotation of your random variables into a space that like all the random variables in the new space now are kind of like uncorrelated to one another, and then like you can just sort the like variance of this yi here, and the ones with like the biggest like variance will be like the principal component. Then you may keep the highest several of them, and then you can discard the rest. Then that's basically PCA. Yeah.
But we should know first P Hermitian. P Hermitian first.
P.
We should know that.
Yeah, you need to. But this you can. Okay, theoretically you have the x here. You can from the data you can estimate the coherence matrix, right?
Yes, that's right.
Once you estimate coherence matrix, you can find the eigenvectors of sigma, right?
Yes, that's right.
Then that will give you your p here. Yeah, that's it. Yeah.
Actually, x in there is metric or vector?
X is a
Metric, a vector.
It's a vector. X is a vector. But sigma is a matrix, right? Sigma is n by n. X is a n by 1.
How to create sigma from x?
So that sigma will be the ij element or sigma is just equal to expectation xi xj, right?
Yeah, that's right.
So if you have a data here, you can just approximate like xi, for example, like
Yes.
yes.
How to?
I mean, like if for example, like if you have a set of data, like how do I draw it? Like
1, 2, 3, 4.
like maybe you sample like multiple times. Let me write like this: x1 sample 1, x2 sample 2. So all of this is like
Maybe
number of sample, like k sample, let's say.
Yeah.
I have
Or
k
maybe
sample.
we can just use a real number, only 4, or for factor for x, 4, 1, 2, 3, 4, and then how to get that? Okay. For example, 1, 2, 3, 4 for x, 1, 2, 3, 4, and then how to create the sigma.
1, 2, 3, 4 is not sufficient because each of them is a vector, right? You sample each time this is a vector. Each of this is an n by 1 vector, right?
Oh, okay.
Right? This is an n by 1 vector.
That's 1 by n by, yeah, okay.
Yeah. Then you can approximate this, right? Approximate this as like, let's say x k vector, the I element. Let's write like this. As k I x kj. So it's wait. So maybe yeah, it's okay. I lose the k. Maybe I use a small k. X small k I x small k j and sum over and 1 over k, right? This k is from 1 to big K, right?
Yes.
This just take the
mean that I in there.
Yeah, you have this. Yeah.
So it means that I here. This one.
For example, like here I have k of them, right? Big K, so many of them. In the middle, maybe I have a sample like x k, and this k sample like it's a vector, right? It's an n by 1 vector, right? And then I have an ith element here, the jth element here. The ith element here will be xi k, right? And this will be like xjk.
Yes. That's right. So that's, yeah, that should be 1 by 1 times the xi and until to k. That's right.
Yeah, and then
yeah, that's all.
then you can kind of approximate this sigma, right?
Yeah.
Then using this sigma, you can. Okay, this is a inferior. You can do that. Afterward, I would say like another way to do it because this is typical, not a good way to do it.
Yeah.
Oh.
And we can do that. This is a factor of multiplication. Yeah.
It's not just that but let's look at the PCA like again, like let's say like we do this PCA. Let's say we can diagonalize sigma, and with this eigenvector like generate P, and then I create this Y here, and let's say like okay, what do we have earlier? We have like
We already have Y.
yeah, we have P transpose P is P transpose sigma P is equal to D. But here let me add one more constraint here. We assume that like this P here actually like sorted the eigenvalues. So in the then I have lambda 1, lambda 2 here is the eigenvalues, and I have lambda 1 is bigger than equal to lambda 2, bigger than equal to lambda 3, and so on and so forth. I can always do that, right? Because this P, if I have like not in this order, I can just rearrange the order of this P here, the columns of this P here, such that like I always have the eigenvalues are sorted. So
you want to make the biggest one at lambda 1.
Yeah, I want the biggest one, lambda 1.
And then
Lambda 1
after that,
first. Like let's say lambda 1 is bigger than equal to lambda 2, and so on and so forth. Now with this, then I can approximate like basically I approximate y. I approximate. I have a.
You say approximate because that is equal.
Oh yeah, yes, this is equal. But I say like no, not yet. This is like coming next. So I have y here is equal to this guy here. Now I generate y hat here is an approximate of y. This is where PCA come from. So I'm not going to have to keep the entire y here. I only keep the first couple elements of y. So for example, like I can keep the first. Oh, there's another k here. Let's see. Maybe I keep the first. I have what ijk. I have first the m elements here, right? So maybe I have this y is originally say y1 up to yn here, right? But I from like m plus 1 and so on, I just take it as 0. So therefore, like I have y. Let's say y is equal to this originally. So I have y hat is equal to y1 up to ym, and then I have 0 here all the way.
Oh, so and the ym is y. Y1 and until ym is what? This one? This sorry. This one?
Until here, it's the same as this original y.
The original y.
Yes.
Here?
And the rest I said is to 0.
To 0.
Yeah.
Okay. What for?
Just to reduce the dimension.
Okay.
Because I originally, when I say to 0, eventually it's the same as I'm ignoring all the components for here, right? So for here, I will consider the data here. I mean, or what should I say? For the first m dimension, we'll consider the values there, the projection up to this m dimension here. But like for the rest, I don't care. I don't care the values, therefore I set it to 0. Now we want to claim that like I know that of course y is a random variable, right? Y is a random variable. Each time here like it's different, right? Each time this y1 up to ym is different, and
But that's not reduced dimensions. That's more bigger dimensions than y hat. This is y hat.
no, it's not more.
This is y hat is a bigger dimension than y.
No. Oh, okay, it's the same here. This is all. Both of them is n. This is n. This is y hat is also n by 1.
And how many y to ym? How many?
Oh, m is like between n and 1, right?
Oh. Even this one is p is actually n. Here n.
P is n what?
N plus n times 1 for p.
No, p is n by n. Oh, p is n by n.
Yeah, n by n. So y of course will be times by n will be n by something.
Oh, this is n by 1. Y is n by 1.
Yes.
X is n by 1.
So y is will be n by 1. So y in here only m, because in here n by 1 should be also in here n by 1 too, because you take from this. So this one should be n by 1.
Oh, wait. Let's restart again here. Y, let's say this is y here. Y can write it. Y is a n by 1, right? I just write
n by 1.
Yeah, n by 1. So I write it a vector as a y1, y2 up to ym, let's say, and then ym plus 1, so on up to yn. And this is the entire vector. Now I have a y hat curve generated by like simply for only keeping the first m elements, and then for the rest I just set it to 0.
Why this one should be m? Because we have n by 1 here.
Oh, okay. M is kind of arbitrary. It doesn't matter. It's like P say. You remember what's okay? What should I say? I can't reduce the dimension from n to m.
Oh, I see. Oh, that is just it is choose by us.
Yes, this is what we.
And
Yes,
what
but
we
that's what
want.
we choose. Yes.
Oh,
Yeah, I should say also said that earlier. So you pick whatever m you want. Like so, let's say, but what you're going to do is I'm going to just keep the first m and then discard out the rest. So that essentially is like a dimension reduction, right?
Mhm.
And we want to show this is optimum. Optimum will be in the sense that like the error. If I look at the error, like y minus y hat. So let's look at the error here. The error is kind of like this, right? This is the mean square error, right? And the mean square error, I can, for convenience, I can use the trace operation here. So trace, what?
Oh, trace.
Yeah, trace of a matrix is the sum of all the diagonal element. Yeah, okay. And by the way, trace have properties. It's very useful. Like trace AB is equal to I have like will be just equal to sum of the diagonal element, right? So therefore will be equal to sum over I AI J B J I sum over J. Because this is the A B I element, right? Yeah. So then trace is like sum over that, right?
Trace of sum over that.
Sum over all the diagonal elements.
Oh yeah.
So
it's only diagonal elements, not
yes,
all.
yes, only diagonal.
Diagonal, okay.
And then but then you look at this is the same as I sum over I J B J I A I J, right? This is just number. I can flip this. So then apparently this is the same as I trace.
I and J should be not equal. Should be not equal. I and J, because you only.
No. I and J can be equal.
No, because that is you only get the diagonal.
Oh, let's say like I is equal. No. Be very careful like what I'm doing here. Let me just. We'll start from here again. So I equal to 1 to n, A, B, the ith element. This is diagonal element, right?
I.
Yeah, I.
Oh, okay.
Right? But what is I? I is equal to J equal to 1 to n, A, I, J, B, J, I, right?
Yeah. With J is n.
Yes, that's A, B, I, right? The I element is that, right? Because
but when J is not same with I, how come?
No, it doesn't matter. Like it doesn't have to do with like whether they're the same or not the same. You have A, B, M, N is equal to summation A, M, J, B, J, N, right? This is general, right? It doesn't, now it's only when like, this is like something general, now I just consider when the I element, so M is equal to I and N equal to I, so I have this here.
That's right. So even that's not same, that will be not 0?
I don't know what you're talking about. I actually like, they just sum over, both of them sum over 1 to N.
I mean that I here, I in here is because in I 1 1 2 2 3 3
Yes.
4 4, and because I and I is same. Meanwhile in here J could be 1. Meanwhile for N.
Wait, let me be very careful here. This is I, right? Therefore M is like I, N is equal to I, right? So therefore it's just this. And this is nothing magical here. Like just look at this. ABMN is equal to this, right?
So it means that that there's M and S is I here. So what for J in here?
Oh, this is like the matrix multiplication, right? You have a B multiply that. Then the M n element is like just this, right? You have this, the M row multiply the n columns, right? So the M4 will have element AM, AM1, AM2, AM3, so on, right? So you have your AM1 multiplied by B1N plus AM2 plus B2N, right? AM3 plus B3N, and so on, right? So therefore, it's just this summation, right?
Oh, yeah, that's right. But that is in the form that then this is become one, become factor. This one. That's right.
Oh, okay. This one is general, right? So this is nothing. It's just a matrix multiplication. Like you, and then like you have A, B, I. Now I look at like the ith element. Then like this M and N just replaced by I and I, right?
Yes.
And then it's just this one. Nothing magical again, right? So, and both of them look at like the ij is just sum over 1 to n. They can be equal, they can be not equal, it doesn't matter. But then like here of just number, I can flip that. I can flip the sum as well. Then it become I equal 1 to n, and then bji, aj, aij. Then if you look at that, like this is actually just equal to, if this is equal to trace AB, then this will be just equal to trace BA, right? So therefore the trace have a very kind of nice properties. If the trace AB is just equal to trace BA, yeah. So maybe I don't need this now. Let me just erase this, so I can have more space. So I put a trace here because this is just a scalar, right? If I have a scalar element, trace of a scalar element is just itself, right? So, but then because I have trace AB is equal to trace BA, and of course trace I can put into the expectation here, so I can have like expectation trace y minus y hat transpose y minus y hat. So therefore it's equal to expectation trace y minus y hat transpose. So I can flip the order now. So then I can put back the trace outside. And expectation y minus y hat transpose. But now then this is actually, you look at that, it's become the coherence matrix. I have the trace of the coherence matrix, right?
Why?
Huh?
This you already done there, but in there also it should be go there. In there.
Oh, okay. So no, this is not trace of coherence, but this is like sorry. I shouldn't say this is trace of coherence matrix. This is what is this? This is like
this one already done like this. This one already done like this because you already So this one also same with this. That's right. So why you put again E here? Because you already have this one. Okay.
Oh, that's different. You look at the transpose here. Yeah, the position of the transpose is different. Yeah, I need to trace because I need to trace to be able to kind of like switch the order of these two things here.
Okay.
So I put a trace here, therefore the order can be changed. Then I can pull back the trace outside now. But if I look at this one here, this one is quite what's that?
But why it can be changed?
Hmm?
Oh yeah, yeah. We
Yeah,
already
because
talked
I
before.
showed that, yes.
Yeah, yeah, okay. Yeah, that's right. And then
And then, oh, well, and then actually we are over time. So, oh, yeah. And then I'll just give you the result here. This is actually just equal to, if you think of that, like, what's the, oh, I guess I need to fill in some step, like in the notes I didn't fill in the step. So this should be just equal to, what was y and y hat? Like, remember, y is the entire vector, y hat is like the vector with only some of this is leaving out. So y minus y hat is this part here, right? It's this part left behind. And they are all kind of like, remember, like, they are all uncorrelated, right? So the off diagonal term is all equal to 0. Oh, let me write it down maybe. Y minus y hat, I got a vector like this. It's like 0 up to 0 y m minus y m plus 1 y n, right?
why that would be change switch?
Oh, because it's y minus y hat. Y hat is equal to this.
Yes, that's right.
Y minus y hat. So therefore, like,
Minus y hat.
the first m element will be cancelled, right? And then the remaining will be just left behind, right? So I have y m minus 1 y.
Oh yeah.
And then this I have like also 0 y m plus 1 y n. Now expectation of this guy, those guys are all uncorrelated, right? I know y is all uncorrelated. Then I basically have some 0 of diagonal, and the first m element will be 0. And then I will have this, starting from this one on, will be lambda 1, lambda n plus 1 up to lambda n, right?
That's right.
Yeah. And then I compute the chase of that, therefore it's just equal to lambda n plus 1 plus up to lambda n. No, so and this is true like for I mean, like, what should I say?
So we have trace now.
We have now the, okay, let's go back to what we want at the beginning. We want to find the error now. I want to argue like this is the minimum error to keep like just m dimension. I mean, like a minimum error for dimension reduction, because for any other, for example, I can discard any other elements, right? But if I discard any other elements, the kind of error will be bigger, right? Because we already sorted the eigenvalues here. So we already know like this m plus 1 up to lambda n here. The sum here will be the smallest amongst if I pick any other group and add them together.
So it means that if 0 is more bigger, is more large, so that this will be trace also will be bigger, will be more, will be less than that. That's right. If we put 0 in here more, if we put 0 in here more, I mean that this is maybe,
yeah, that would be bigger, yeah.
M minus 1 in here.
Yeah.
So 0 in here will be more. So the result in here will be
It will be bigger.
Bigger.
Yeah. But for good comparison, you should keep the same dimension, right? So I reduce to dimension m. So I also like should, for whatever reason, I should keep the same number of non-zero elements, right? So I should keep the first m, as you can see, because the first m actually will give me the minimum expected error. Because if I for example, I remove some of this here and keep one of this here, then my error will be instead like maybe I remove like this one. I'm at lambda 1 here, right? Something like that. Instead of like keeping y1 here, I remove y1 and keep a ym plus 1 here, right? Let's say. Then my error will become lambda 1 plus lambda n plus 2, plus lambda n. And of course, this will be bigger than like lambda bigger equal to lambda n plus 1 plus lambda n, right?
So we should short the lambda actually. We should short that.
Yes, lambda here we assume that we already sorted like here.
Already sorted.
When we already assume it's sorted.
Okay.
So if we assume it's sorted, then we should simply keep the first. If you want to reduce dimension to m, then we should only keep the first m components, and then I discard all the rest.
Yes. So it means that if we have got a bigger m, I mean that if we bigger this one, so the error will be less.
If you keep m is bigger, you mean?
I mean that if this is m now become m plus 1, so this will be less because you short that already done.
Yes, we already shorted that. Yes.
So, okay. So it means that something like if we reduce less the dimension, the error will be less. That's the conclusion. If we reduce less, if we just reduce 1 or not reduce at all, so of course our error will be 0 because all of dimension we take all. That's right.
The conclusion is like if we want to do a dimension reduction from let's say n dimension to m dimension,
Yes.
then we should keep the components with the largest eigenvalues
Yeah.
first, the m largest eigenvalues, and discard the rest,
Yeah, that's right.
and that will give you the smallest expected
Smallest
error.
in,
Yeah.
in below.
Yeah.
You should largest eigenvalue
Yeah.
above.
Yes.
Yeah, that's right. So we have small error then.
Yes.
Okay.
So okay, I should really stop here. So yeah, I don't have time. Yeah. Okay. So I won't leave homework today. So there no homework like until I guess the quiz or like exam or midterm or whatever you call that. So we'll have class next week again, and then okay, I will talk to you guys then.